So last video we looked at Ernest Rutherford's experiment and how it caused a shift from J.J. Thomson's plum pudding model to the planetary model. So based off of Rutherford's experiment, he determined that those electrons must be outside of the nucleus, which is positively charged. That was Rutherford's model of the atom. Now another student of J.J. Thomson's was this gentleman called Niels Bohr. Now Bohr also worked with Ernest Rutherford, and Bohr knew that, based off of Rutherford's results, that the positive nucleus must be surrounded by negative electrons. The change to Rutherford's model came with how Niels Bohr described the electrons' positions. So based off of Rutherford's model now, there's a problem with where the electrons are. Based off of Rutherford's model, those electrons could be anywhere, and those electrons are orbiting that positively charged nucleus. So we have our positive nucleus here, we have our negative electron out here. We look at this shape and we know that when something orbits, we call that a centripetal force, that's center-seeking force. In this situation, it's an attraction between a proton and an electron. It's also called the electric force. So based off of Rutherford's model, this is what's keeping those electrons in orbit. Now if we think about centripetal force, that centripetal force is mass times our acceleration. And in this situation, we have a centripetal acceleration causing that electron to orbit around that positive nucleus. Now this caused a problem. If the electrons were anywhere, they would eventually spiral in and crash. The reason for that is because if we know that an electron is accelerating, while accelerating charges produce electromagnetic radiation. So there's going to be energy coming off in that model. In fact, as the electrons spiral, they should go faster and faster and release their energy in ever-increasing amounts. Now, that's based off of this equation. The energy is Planck's constant times the frequency. This would mean we should see a bunch of increasingly higher frequencies of EMR being given off by atoms all the time. But we don't. Instead, experiments showed that atoms only ever emit energy at specific frequencies. So this must mean that specific, discrete amounts of energy are actually being emitted. So this model doesn't work. The fact that we don't see higher and higher frequencies of light coming off of those electrons, and the fact that those electrons don't spiral down to this positive nucleus, and atoms don't just spontaneously implode, means that this planetary model is not 100% valid. Now, the location of the protons works. We know the electrons are outside, but we need a better explanation, a better understanding of what those electrons are doing in the outside, in the outer edges of that atom. And that's where Niels Bohr came up with this model. Now, this was one of the ideas that he used to formulate his model. Another was based off of something called spectroscopy, which was kind of groundbreaking at the time. So physics at this time started to look at different elements and the light that they actually would emit. There's certain frequencies that each element would give off. And actually each element gives off its own specific frequencies. It's kind of like a fingerprint for an element where we can actually identify elements based on the actual frequencies that are given off. They don't give off, if we take an elemental gas, they don't actually give off just white light. They give off a certain color of light which is a combination of different frequencies. In the next video, we'll look a little bit more at spectroscopy and how we can end up with these different types of spectrum, continuous spectrum, an emission spectrum, and an absorption spectrum in a later video. But for right now, it's just important to understand that spectroscopy was something that was going on at the time. And it provided evidence for Niels Bohr's model. One man who did a lot of work with that was Gustav Kirchhoff. So he proved that every element and compound had a unique spectrum that could be used like a fingerprint, and he was actually able to identify previously unknown elements. On the left-hand side here, there's some different examples. Different spectrums that we get from different elements. You'll see that the spectrum we get from hydrogen is different than the spectrum from helium, which is different than the spectrum from mercury. So by analyzing the light that's being produced from these different elements, we can actually identify what elements are present. For example, we have an absorption spectrum here from a star. And then we also have the absorption spectrum for the element of hydrogen. You can tell looking at the absorption spectrum from this star that it contains hydrogen, because these bands, this one, this band, and this band, as well as this band, correlate with what we would expect to see if there was hydrogen gas present. Now you'll also notice that there are some bands that don't show up in hydrogen. So whatever this star, whatever the gas is surrounding the star, well, there must be another element there as well. And that's what spectroscopy was looking at the different frequencies of light that are emitted from different elements and identifying the elements that were present. And again, in the next video, we'll look a little bit more at how these different spectrums are produced. But Niels Bohr used this as evidence for his model as well. So this, combined with the idea that electrons can't be located anywhere, led to Niels Bohr's model of the actual atom. So he described electrons as not spiraling. So they don't spiral into new orbits, emitting energy continuously, because we don't see that. Instead, Niels Bohr said that they jump. And they only jump into and out of very particular orbits, as governed by Planck's constant. So again, you think of Planck's constant, we have this relationship between Planck's constant and energy. So electrons only exist at certain energy levels. And that was Niels Bohr's big discovery. It had led to the quantum movement. It went from that classical model of the atom, and it was beginning to get into the quantum realm. So he described electrons as existing at these different levels. And instead of spiraling from one level to another, they jumped. If an electron, you'll see in this diagram, falls from this energy level to this energy level, well, that electron has lost energy. That energy has to be conserved. So you'll notice that there's EMR given off. And we can calculate the amount of energy, or that change in energy. It's Planck's constant times that frequency. That equation we have for energy when we're talking about light. So this was Bohr's model, based off of kind of the fact that these electrons could not be anywhere because they would constantly emit EMR and they'd spiral down to the nucleus, and that model would not hold up. So based off of that, and based off of what scientists were actually seeing with spectroscopy, that each element had its own unique fingerprint. When it came to the frequencies that were given off, Bohr came up with this model, where these electrons, these shells, are different energy levels where electrons can exist. They can't exist in between. An electron cannot be located between the third and second energy level. It can only be found in a stable state either on this level or on this level. Now, just like electrons can fall down and release energy, that's how we get some of those different spectrums, electrons can actually jump up as well. If I have an electron on this second energy level, and a photon of light comes in and hits that electron can jump. Where now it has enough energy. As long as it has enough energy, it can jump up to this third energy level. And now this wavelength of light, part of that energy has been given to that electron to jump up. So now that wavelength of light will probably be longer because it has less energy now, and will travel off that way. And again, if that electron falls back down to the second energy level, it'll emit a certain frequency of light as well. So that was Bohr's model. That shift from this planetary model of the atom to this quantum mechanical model, where those electrons can only exist at stable states, and they jump according to very discrete amounts or quanta of energy. According to Planck's equation, E equals hf.